All right, Chem 11. Welcome to the first lecture of our solutions unit, the nature of solutions. This PowerPoint was just added to your D2L site, so you can download those notes. We'll be doing half of this slideshow today, the other half tomorrow. So there's going to be 2 YouTube videos to go along with the one PowerPoint note. As always, that's what's up on the iPad. The rest of the whiteboard will have diagrams and things that will help us out along the way. So, we're going to talk about solutions today and what they are and types of solutions and the components of a solution and all that sort of stuff. Get our feet wet in the basic terminology of the whole thing and then start to go from there and expand on it. So, solutions, they're not pure substances. They look like they should be because there's only one phase, right? But they're actually a mixture. If you remember from grade 9, matter breaks down into pure substances and mixtures. And then within the mixtures, there's homogeneous mixtures, which look the same throughout. And then there's heterogeneous mixtures, where you can see the different pieces and parts of them. A pizza is a great example of a heterogeneous mixture. I can tell the pepperoni different from the cheese, different from the sauce and the crust and so on. A homogeneous mixture would be like Gatorade. Gatorade has the electrolytes in there in the form of salts. There's sugar in there, there's flavor crystals in there, and there's water, obviously. But all of these components mix into something that looks like it's all the same throughout. This orange or red or blue liquid, right? There's no, you don't look at a glass of Gatorade and go, oh, look, I can see all the different levels in there. It all combines and looks like one substance. The components of a solution are right here. We've got the solvent. And the solvent, in this note I say liquid because more often not in lab work that we're going to be doing, liquid is the liquid of some sort, usually water, is that solvent. But the solvent doesn't always have to be a liquid. A solvent can be any of the other states as well. It can be a gas or a solid. We'll see later on in this lecture how that happens. The trick with the solvent is usually there's more of the solvent and it acts as the dissolver. It's the thing that does the dissolving. The solute, on the other hand, is the thing that there tends to be less of, right? The solute gets dissolved by the solvent, right? So it's the dissolvee is, if one's the dissolver, we have the dissolvee. It's the thing that gets dissolved, the solute is. If the solvent is water, then we call that solution an aqueous solution. And we talked about this AQ, when we did the solubility rules. And they'll be put back into play in this unit as well. All right? So, when we talk about whether or not something can form a solution or not, we have to talk about solubility. Now, solubility is the ability to dissolve, right? So if I am soluble in water, it means if you add me to water, I will dissolve. If I don't dissolve, I am insoluble. So if you look at things like salt or sugar, the salt or the sugar will dissolve in water. Give it a little shake or a little stir, and it's going to mix no problem with that. Salt and sugar are soluble. Now, if I add something, and I'm going to use those solubility rules we just mentioned, if I add something like calcium sulfate, or if I add calcium phosphate, these are things that do not dissolve. You drop them into water, they stay together, they won't be pulled apart, they don't dissociate or fall apart within the water. They stay strong, they stay together as a solid, right? So if something is insoluble, it means it's not going to dissolve in a specific solvent, whether it's water or ethanol or oil or whatever it happens to be, right? Now, there's special terms used for liquids. So I'll use the blue for a liquid. If I have 2 liquids and the 2 liquids will dissolve within each other, they are said to be miscible. If they do not mix with each other, they are said to be immiscible. right? Miscible and immiscible are only when we have two liquids. But miscible is basically like saying the two liquids are soluble. Immiscible is like saying the two liquids are insoluble. But they're only used when we're dealing with two liquids. All right? Now, for the type of solutions, excuse me, the type of solutions, we're going to go back to the various states. All right? So that's what we're going to be talking about here. So our first example, you know, if you have your iPad, you can zoom in on the pictures a little bit more if you have these things at home. The first one is a very common one. It's taking a solid, and solids don't have to be like a solid rock. Powders, crystals, those are solids as well, right? A lot easier to dissolve those. So taking a solid and dissolving it in a liquid like water. Here I have salt water, ocean water, right? So you would have the actual salt and minerals of the land, which is solid, dissolved in the liquid water, right? So salt water is, right, ocean water is a great example of a solid and liquid. Oh yeah, and of course Kool-Aid, right? Kool-Aid and all its, you know, flavorful yumminess. Inside of there you got sugar, you've got the coloring, whatever that happens to be, whatever color the Kool-Aid is, you've got the flavoring, right? And of course the water. So you've got these different components in there, but again, they look like all one phase. And when you buy Kool-Aid crystals, they are solid, and we dissolve them in liquid water. Another common one, liquids and liquids. Any type of alcohol-containing beverage, beer, wine, rum, vodka, whatever, there's a liquid called ethanol dissolved within the water. And when you talk about beer being 5%, that means for every 100 mils of the solution, 5 are ethanol, the other 95 are water and flavoring and that stuff. If I look at vodka, it's 40%. That means out of every 100 mils, 40 of those mils is the ethanol. The other 60 is the water and the flavoring and whatever else, right? So that's a great example of liquids dissolved in liquids. Gasoline does the same thing. It takes ethanol and dissolves it within octane, right? Octane is the major component there that burns in your car's engine, right? Propels you forward. Another common one, gases dissolved in liquids. So here you see a Coca-Cola, and Coke is a carbonated beverage, which means carbon dioxide gas is dissolved within the liquid, within the water of the pop, right? So carbon dioxide is dissolved within water. And of course there's other agents in there, coloring and flavoring agents. And there's some sparkling apple juice, of course. No, that's a beer. I know you know that. So here's a beer. Again, it's a carbonated beverage. So it has carbon dioxide bubbles that are dissolved within the solution, the water. Gases can also be dissolved in gases. We breathe this in all the time, right? The air we breathe is a mixture, a solution of nitrogen, oxygen, carbon dioxide. There'd be trace amounts of methane and nitrous oxides in there as well. So gases, right, can mix with other gases. In our atmosphere is a number of clear, colorless, odorless gases, and they all mix together. So we can't see a difference. It continues as one phase. Now, here's an interesting one. You don't have these, I would doubt, but your parents might have them. And what it is, it's called an amalgam. This was a material that dentists would use for fillings back in the day. Not your day, my day. I've got a couple of these. Your parents and your grandparents would likely have some as well. And what it was, right, it's a liquid dissolved in a solid. And that seems weird. You mean a liquid dissolved within solid. Usually the solid gets broken down by the liquid, but here the liquid was mercury. And what happens is they mix the mercury with a mixture of silver, copper, and tin. These were the solids. And together the two of them would make this solid compound that they would form inside of your tooth to fill, you know, depressions and openings, cavities, right? Solids and solids. So I'm just going to erase this. Here we see a metal rim on a car. Now this is a high performance automobile. You can buy custom parts. So quite often what they want to do is for car parts, they use things called alloys. An alloy is a solution of metals. So basically what they do is they take two or more metals, melt them down, mix them together because they're now in a liquid. It's easier to stir them together when they're liquid, pour them into casts, and then cool them down, and they harden and solidify into the various parts. In this case, it's a fancy rim on a high performance vehicle. And so what they do with some of these parts is, right, for the car parts, is they'll take one metal. Metal number one is the strength metal, right? That's adding the strength and the durability. Number two is the malleable metal. Malleable means I can form it in different shapes quite easily, right? Right? And they also tend to be lighter and less dense. So what happens is if I have a part that I have to put on a car like a rim or another part of the car, if I use metal number one and only metal number one, yeah, it'll be very strong, but it'll also be very, very heavy. And that extra weight slows down the car, right? The horsepower kicked out by the engine has to move more weight now, so the car doesn't go as fast. But if I make an alloy and mix two metals, melt them down and mix them, I can get the benefit of the strength from the first metal and then the lightness, right? It'll lighten it up, and it's also very shapeable or malleable, which I can make a custom look for my vehicle. So I get the best of both worlds here by combining the two solids, the two metals. We do the same thing with brass. If you look on the periodic table, there is no element for brass, right? I think brass is a combination of, and don't quote me on this because I'm not exactly sure, I want to say zinc, copper, and nickel. Could be totally wrong. I know the copper's in there, but it's 3 or 4 metals mixed together. They melt them down, and then they form the various parts, like our French horn here, right? And of course, you can make grills with alloys, right? Nice job, bud. Anyway, there are some that are missing here, right? Now, there's 3 situations that are missing from these diagrams that I'm going to go over quickly. They do exist, right? But we don't really ever see them in the lab, in our lab that we're doing anyway, the labs that we do. So what's missing from our list here? The first one is solid in a gas. You're thinking, wait a second, a solid in a gas? How does a solid dissolve within a gas? Well, we see it all the time. Gases are used in aerosols. Now, usually aerosols, if you think about an aerosol spray, it's a liquid that's dissolved within the high-pressured gas. You push the release valve on top, and it sprays out, and you get your hairspray or your Axe cologne, whatever it happens to be. But there are also aerosols that use solid dust-like materials inside of that compressed gas, right? And so when you pull the trigger on the canister, it propels the dust-like material that was on the inside outward, right? The reverse of this, a gas in a solid. So a gas in a solid, it's pretty common, or my example, sorry, is pretty common. We don't see it a whole lot. Ice, right? In grade 10, you talked about ice cores being taken from the Arctic, and they'd analyze the little bubbles, the little pockets of air trapped in there, right? Those little pockets of air contain gas locked in the solid water of the ice, right? So that is an example of a solution that has a gas dissolved within a solid. And some of the air pockets are very, very small, right? And then the last one is a liquid in a gas. All right, so we got a liquid and a gas. I'll underline these states. These 3 are not in there, but they do exist. So a liquid in a gas, well, humidity is something that is coming to effect now, right? The weather's getting a little bit nicer, and any of the rain that falls, it then evaporates and joins the air. What humidity is microscopic H2O droplets that are in the air. And so what we're measuring is, if humidity is 80%, it means the air is holding 80%, or is at 80% capacity of the amount of water that it normally could carry. The higher the humidity, the more uncomfortable and sticky it is, because your sweat isn't able to evaporate from you and join the air, because the air is already saying, look, I'm pretty full as it is. I don't have room for the moisture of your sweat. So your sweat stays on you, and that's why it's sticky and hot and uncomfortable when it's really humid. When the humidity drops and the air is dry, right? I'm using air quotes, dry. Those are great working days, because if you start to sweat, the sweat has lots of room now in the empty, dry air to go into it and leave your body taking the heat with it. So you're able to cool off easier. Now, solubility. Solubility is the ability to dissolve. Something that is soluble can dissolve in something else. Solubility is the ability to dissolve. So solubility is the ability to dissolve in something else, right? And we can measure how well you are, how well you dissolve in something else. So we can take a solution, we can take a solvent like water, right? And we put one molecule in there, and it dissolves okay. It doesn't do an amazing job, but some of it dissolves, and we say, hey, it's soluble, but it's got a medium to low level of solubility. We take a different compound and take the same water from the same source, and we put that in there, and the water's just eating it up. Tons of this stuff is dissolving in there. That's got a high level of solubility. So this is quantifiable. Remember, quantity is using numbers and units. So we can use numbers and units to quantify solubility. We can measure it using numbers and units, right? The more solute that can go in there and dissolve within the solvent, the greater the solubility of that substance. So when we talk about solubility, we're talking about the solute's ability. Oh, spelling ability wrong. Long day. Ability to dissolve. All right. So you keep adding stuff to this solution. So for example, let's say we had a beaker of water, right? Not a far stretch for a science class. And we take salt, right? I'll try to draw a salt and pepper shaker in here, right? And we take salt and we put it into the water, right? So we shake in a little bit of salt. The salt has no problem dissolving in water. Salt's really soluble. And we keep shaking it and shaking it and shaking it, and more of the salt is occupying the spaces in the water. There comes a point where all of the little spaces are now occupied, and no more salt can go in. We've reached the maximum for this volume of water. We've reached the maximum number of salt molecules that can go in there. When that happens, we say that the solution is saturated. It's full, right? Now, temperature has an effect here. We're about to talk about that. But for a given temperature, there's a certain amount of solute that can go in a certain volume of water. And when you reach that certain amount of solute, it's called saturation, or a saturated solution. What happens if I reach my saturation point and I continue to add salt? Well, what will happen there is the salt will actually not dissolve, and the crystals will just drop to the bottom of the beaker. So if this was my saturated solution and I continue to shake the salt shaker in there, I would end up with a little hill or pile of salt at the bottom of the beaker. There's just no place for it to go. All of the spaces in the water are occupied, so it's just going to sink to the bottom, and that's it. The solution is saturated. There's no space for this extra salt. So when we talk about solubility, a solution can be unsaturated, which means you haven't reached that maximum saturated amount yet. If it's unsaturated, there is still room for more. So when we first start shaking salt in here, it's an unsaturated solution. The first couple of shakes isn't going to occupy all the spaces. Then we reach the saturation point. In a saturated solution, we just discussed this on the previous slide, is when all of the spaces are now occupied. Think of the water as a hotel. All the rooms in the hotel are occupied. There's no more room for any more people. If we put more people in there, they're just going to cluster themselves in the lobby and in the hallways and not have rooms to go into. And they're just going to gather in one spot. Our salt gathered at the bottom here. When we reach this type of a thing, we call it a saturated solution. So now an excess amount of the solute, which is the salt, just sits there. It's undissolved. Or if my solute, in this case the solute was the salt, if my solute is a gas, what happens is the gas will just bubble off and go into the atmosphere. Right? So if we had carbon dioxide and take a carbon dioxide and ran a hose from that tank into the water, carbon dioxide would bubble into the water and dissolve in there. After a certain amount of time and a certain amount of carbon dioxide going in there, it would just start to bubble out of the water pretty easily. We've reached our saturation point, and now the solution is super saturated, and we're just losing carbon dioxide, and we're just wasting the salt here. So when we talk about solubility, we can categorize the solubility, right, or the solubility-ness, if that's even a word, of different solutes, of different materials, based on how much of them we can get to dissolve within 1 liter of water. So solubility, we often talk about how many grams can we get in 1 liter of the solvent. So if something is considered very soluble, that means we can get more than 100 grams. This little table describes it. We can get more than 100 grams in a liter. The water, the solvent just eats it up. If we say something is just soluble, not very soluble, but just soluble, it means we can get between 10 to 100 grams in there. Right? Anywhere from 10 to 100 grams. Yeah, that's pretty soluble. You know, it's a soluble material. If we can only get from 1 to 10 grams, we say that it is slightly soluble. So we have our liter of water, and we get 5 grams in there, and that's it. That's all we can get to dissolve. We say it's slightly soluble. It didn't dissolve in there very well. There was not a whole lot in there. Only a little bit did. And if it's less than 1 gram or none at all, we say it's insoluble. Look, it's just not mixing in here. It's not dissolving, right? If I take, pieces of copper, if I take pennies or iron filings and I dump them in here, they're insoluble in water. They're not going to dissolve, so they just fall to the bottom, right? They're insoluble. Now, we said temperature, right, has an effect on solubility. So what does temperature do? Because we know temperature, we measure it in degrees Celsius. It has an effect on solubility. Well, that depends on what the solvent is, right? And what our solute is. So there's a few different situations, and I'm going to describe them on this slide. I'm going to erase this because we are going to write a couple of things here. So the first situation, right? We're talking about solubility, the ability to dissolve, and temperature. I'll put temperature in red because it makes us think of heat. All right. So our first scenario, for solids. For solids, solubility increases as temperature increases. What that means is, let's say I had a bucket of water at room temperature, say 20 degrees. I could shake the salt in there and a certain amount would go in. Now, if I put that bucket of water on the stove and raise the temperature, let's say I put the temperature up to 80 degrees, so a 60 degrees increase over the original 20 degrees. If I put it up to 80 degrees, I actually can get more of the solute in there. The solubility of that material at a higher temperature increases. So I'll get more salt in the water that is hot than I will in the water that is cold, right? And what happens is the water molecules with the heat start to bump and move quicker, right? If you remember the kinetic molecular theory, I think from grade 9 or grade 10, I think it's probably grade 9 you do it. When you add heat, particles move faster, and the spaces between them increase in size, which means there's more spaces in the hotel and more of the solid solute can duck in there and take those spaces up. When it's cold, the spaces are smaller, and so less room for less solute. Now gases. Gases are the exact opposite. If we're looking at gases being dissolved, right, the solubility of a gas actually drops as the temperature goes up. So this is an interesting thing. These two solids and gases, they're the exact opposite. Solids, you can put more in when the temperature's higher. Gases, hot water holds less gas. This is important, for ecologists and environmentalists, because as climate change occurs and the average temperature of the Earth, and there are bodies of water on the Earth that have oxygen dissolved in them for the fish and for the other aquatic creatures, as those bodies of water increase in temperature, it means that they can hold less gas. The solubility level for things like oxygen, right, it drops, which means the water has less oxygen, and oxygen is something you need to live. So hotter bodies of water often are deadly for aquatic organisms because they hold less oxygen and they asphyxiate. Fancy word for they basically choke because there's not enough oxygen to breathe. There's not enough oxygen dissolved in that water. Now our third scenario. Our third scenario are liquids. Now liquids are kind of an odd one here. Liquids, there's no definitive pattern. Some liquids get better with higher temperatures, some liquids do not, right? So some liquids act like solids, other liquids act like gases. So there's no definitive pattern here, they just do what they want. Each liquid has its own sort of pattern. Some will increase, some will decrease, all right? But these two tend to trend pretty much all the time that way. So here's a graph here, and this graph shows the temperature along the bottom, right? I'm going to do this graph very quickly. So our graph is set up like this, and we have temperature here, right, in degrees Celsius, and the temperature increases as we go that way. And over here we have the solubility, and solubility increases there's 0. So our solid will do in black. Most solids, as the temperature increases, the graphs tend to go like this or like that on various levels, right? Here we have a number of different salts. So sodium nitrate, lead 2 nitrate, calcium chloride, sodium chloride increases only a little bit. Notice, here we have cesium sulfate, and it actually declines. So just like a lot of stuff in chemistry, there are general rules that most things abide by. Every so often, our cesium sulfate shows us there are some exceptions. But more often than not, you can see there's at least some sort of an incline for all of these solids. The gases will do in blue. Here's carbon dioxide, right? Now the solubility level increased for all the solids, but look at carbon dioxide. At 0 degrees, it holds this much. And as the temperature goes up, it goes by tens, 10, 20, 30. As it goes towards 60 degrees, the temperature is increased, but look at the amount of CO2 that can be held. It's decreased dramatically. So CO2 was like this. At cold temperatures, it can hold a lot of CO2, that solution. At warmer temperatures, as the temperature increases, it holds a lot less CO2. That means if you crack open a pop in the winter time, or when it's really cold out, close to 0, and you leave it on the step, you can go back an hour later and it's probably still got its fizz. It still has its snap to it, right? You take that same pop and go outside when it's 30-some degrees in the summer, open it up and forget it on your step, and leave it there for an hour, it's probably going to be flat. because that pop, which was cold out of the fridge, has now increased in temperature, being out on your step, and all the CO2 that provides the fizz in the pop has now left and escaped into the air. And so you go, oh my God, there's my pop I forgot on the step. You go have a drink of it, and it's flat, right? In the winter time, you get a little bit more leeway. So that's all for now. All right. We will continue this lecture. Why water melts witches. Who wouldn't want to know why water melts witches, right? If you ever watched The Wizard of Oz, at the end, that's what kills the witch. Spoiler alert. Anyway, we'll continue this talk tomorrow on our next YouTube video. I said this one video was going to have 2 or 3 videos coming from it. We'll continue tomorrow. I hope everything was crystal clear. If you have any questions or comments, please do so in the comment section underneath of this video. Or if you're one of my students, reach out to me through Edsby. All right. Thank you very much. Hope everything was crystal clear. I'll see you soon. Bye-bye.